Start by sharing my screen. Okay, so what I'm going to talk about is we're going to start the task of studying energy and energy flow by first looking at ideal gases, because that's the simplest case in physical chemistry, or in chemistry, really the simplest system that you can get. So some of this, so I guess I'm going to start talking about gases. And so a lot of this is review from Chem 104, if you took it at Rhode Island College. Sometimes gases are taught in the first semester of Gen Chem. It depends on where you take it. But so what we're going to do is do a lot of the same sort of information that was taught in general chemistry, but we're going to sort of make our definitions kind of more specific. And also we're going to consider gases and their properties a little bit more mathematically. You know, realizing that, you know, this might help us along the way in this course, because there's a, you know, that's what we tend to do in PChem, is look at things more mathematically. So I'll just start with a very fundamental question. What is a gas? And I'm sure if you were in person, you would tell me that a gas is a form of matter that fills its container. It's the only form of matter that does that. Liquids don't expand to fill their container. Solids have their own shape, but a gas will literally occupy the entire container. This is kind of what I would refer to as the macroscopic definition, because it's talking about what that gas as a whole would do. But I'd like to, for a moment, write something of a microscopic definition. And whenever I say microscopic in this class, what it means is from the point of view of the particles, from the point of view of the molecules. So, from the point of view of the molecules, let's see, hold on. From the point of view of the molecules, a gas is a form of matter where there's a lot of space in between the particles. So I'm just going to write lots of space between molecules or atoms or whatever the gas particles are, you know, depending on whether you have a compound or an element. Okay, so that's basically the idea of what a gas is. And now I'd like to talk about what we call the fundamental properties of a gas. And, you know, you can guess what some of these are, right? We have pressure. The gas can have volume, temperature, and then this N here is the number of moles. So what I'm going to do is go through each of these sort of one at a time, and to make the, like I said, talk about it in a bit of a more specific way. So I'm going to start with the easiest ones to talk about, which are the volume and the moles. Okay, we know what the volume is because gases expand to fill their container. So the volume of a gas is equal to the volume of the container. So really nothing could be simpler than that. The type of units we use in chemistry and physical chemistry, we use liters most of the time because gases occupy larger volumes, but of course milliliters and etc. We could use other things, but those are basically the units that we use. And N being the number of moles. Well, if you take the mass of a gas and you divide it by the molar mass, so M over, I use this fancy M for the molar mass here, that gives you the moles. So, you know, if you know what gas you're talking about and you are able to get a mass for that gas, you simply divide the mass by the molar mass and you'll get the number of moles. So we're really done with volume and moles, easiest of these fundamental properties. And now we're kind of up to pressure here. So pressure is a little bit harder. Okay, so what is the definition of pressure? So when I teach this in class, I'm going to ask you, and I very much hope that somebody tells me that they learned in physics that pressure is force per unit area. Okay, and I'm going to give you a little bit of an example in a minute, but I want to mention that what we call this SI, that's the System International, the SI unit of pressure, which I'm sure you remember from physics, is the Pascal, or given the symbol PA. So a Pascal, 1 Pascal, is 1 Newton, that's the unit of force, per meter squared. So force over area is units of force over units of area. A Newton is a kilogram meter per second squared. Now, how would I know that? Supposing you needed to know what the unit for force was on some sort of exam, and you didn't remember that it was kilogram meter per second squared. What would be, an easy way of figuring out what that unit might be? And so what you would do is you would think about Newton's second law, that F equals ma. So you would know that force is a product of mass and acceleration, and that mass can be in kilograms, and acceleration, well, that's meters per second squared. So if you put that all together, kilogram meters per second squared, that is your unit of force. So even if you didn't know that that was a unit, you could sort of figure it out by knowing Newton's second law. Okay, so it's important to think about the units of things. So let's see. If a Pascal is 1 Newton per meter squared, should write that a little better, meter squared, and a Newton is a kilogram meter per second squared, that means that a Pascal is also equal to this. And you'll notice that one of these meters cancels. And, if you take a kilogram per second squared and you divide it, that's like multiplying it by 1 over meters. So that's a kilogram per meter second squared. So a Pascal is also a kilogram per meter second squared. And I have a special problem on the barometer. And this is actually the first question. So you can use your notes for that. All right, so I wanted to give you an example. So let's suppose we have a table. Find out how poor an artist I am as time goes by. So here's my table. I have a little bit of a leg sticking out there. And let's say I have a poster board on this table that's square. And let's say it's 1 meter squared. So I have poster board. That's 1 square meter. And suppose it weighs 100 grams. So that's about, a little less than 1/4 of a pound. That seems reasonable. So that's 0.1 kilograms. Okay, now force is mass times acceleration. The acceleration due to gravity is 9.8 meters per second squared. So it's approximately 10. And I'm going to use 10 because this is like a back of the envelope calculation, a very, kind of rough calculation. So the force exerted by this poster board, let me get myself a little more space here. The force exerted by the poster board would be my 0.100 kilograms, the mass, times the acceleration, 10 meters per second squared. And I'm going to divide that by the area of the poster board, which is 1 meter squared, right? And so 0.1 times 10 basically is 1. This is 1. I'm not paying much attention to sig figs here. 1 Pascal. So if you want to understand what a Pascal is, just think about a 100-gram poster board on a table exerting that downward pressure due to gravity. And that pressure is 1 Pascal. So I guess my next question is, or the next thing I'd like to think about is, how does this compare to, for example, the pressure in the room, right? Because this course, we really deal with pressure of gases. So how does 1 Pascal compare with the pressure exerted by the gas molecules in this room? Okay, and I always like to give the answer to this question because it seems to me so very counterintuitive and just out there. So the pressure in the room is approximately at sea level, because we're almost at sea level here. It's usually generally about what we call 1 atmosphere. And 1 atmosphere is 101,325 pascals. Okay, that's approximately 10 to the fifth times the pressure exerted by a poster on that meter squared of poster on that meter squared of table. So I mean, I find that absolutely astounding. It's just so much higher than I might have thought. But anyway, so the units that we use in this class, and the reason we use these units is because we deal with atmospheric pressure. And so we're not going to be talking about pascals very much. What we use is we use the atmosphere. And 1 atmosphere is 101,325 pascals. We also use the bar units, especially later in the semester. 1 bar is actually 100,000 pascals, or 10 to the 5th pascals. And so you could see that an atmosphere and a bar are almost the same. 1.0132, oops, I shouldn't write that there. 1 atmosphere is 1.01325 bar. Okay, all right. So those are units we use, but there's another unit we use, and that's called the millimeters of mercury, or the torr. Okay, let's give it a little t, even though it's named after Torricelli. Okay, and look at this. This is a length unit, right? How does a length unit come to be a pressure unit? Okay, so that's the next question. So why a length unit? And so what this actually is, so 1 millimeter of mercury, or 1 torr, they're the same, is the pressure exerted by a column of mercury that is 1 millimeter tall. Pressure exerted high. Okay, It's very convenient that mercury is a liquid and has such a nice high density. So it has made it a very useful substance for measuring atmospheric pressures. So 1 atmosphere is 760 torr, 760 millimeters of mercury. Okay. By the way, in this class, I tend not to use pascals very much, so I don't need you to use them either. So what I want to do is show you a picture here. This is a picture of a Torachillian barometer, otherwise known as just a barometer. And I know that this one on the right here is really hard to see. So I have this schematic on the left of what's going on here. So there's actually a reservoir down here of mercury. And then there's this column as you go up. There's literally a column of mercury in here that goes up to a certain height. And maybe this is the top. This looks like it might be the top, but it might be something else. I think that's not the top. I think that's like another device on top of it. Yeah, that's the device for measuring it. Actually, you can see the top here if you, I don't know, it's probably not possible to see, but I think it's sort of what it looks like on top is kind of rounded, because mercury is more attracted to itself than to the walls of the container here. So it's not like water that's attracted to the glass in the burette, and so it coats the glass in the burette. So water looks more like, you know, it has a meniscus like this. Water has mercury has a positive meniscus because it is not attracted to what it's in, to the metal of this container. But anyway, so this is a barometer. So how would you set up a thing like this? So what you could do is take a long column of mercury, like what's shown in this part of the diagram here. Make sure it's all filled with mercury. Obviously, that's not how it's done here because you have this tiny little reservoir, but this would be a way of doing it. And if you then inverted this column of mercury with the open end down here and the closed end up here, right, then this is what would happen. The mercury would go part way up, just like it's shown here. There would be a space on the top here. The mercury would go part way up. Okay. So the question is, why does the mercury only rise to a certain level? Why doesn't it completely fill it? Or why does it go up at all? Just get the, okay. Why does it only rise to a certain level? Why does it go up at all? Why doesn't it just sit here, you know, with the same level here? So why not this? Okay, and so in order to answer this question, we have to think about the forces that are involved. Okay, so if I draw my mercury in the pan, right, here's the inverted cylinder. Obviously, I'm not making it high enough, but that's okay. Right, and you know, I have a certain level in here. What's going on is that the atmospheric pressure is pushing down on the mercury in the pan, and that is causing the mercury to go up. So the force due to the pressure, right? So remember, pressure is force per unit area. So that means that the pressure, the atmospheric pressure, multiplied by the area is the force, okay? That's actually the force pushing up. But there's another force that's at work here. And that other force is gravity, which is going to push down. So if I draw a force diagram, I'm going to have the force going up, which I'm just going to call P ATM times A. That's the force up. And then, just put a little arrow here. And then going down, I have mg, which is the force going down. So when you look at this barometer and you see that the level is not changing here, there's a particular level that, you know, maybe initially the mercury goes up, then it stops. It stops. That means that the level isn't changing. So when the level stops changing, which really happens pretty instantaneously, it means these forces equalize. So it means that this PA, this is the atmospheric pressure, is equal to mg. Okay. And so what I'm going to do is find a relationship between the pressure exerted by the atmosphere and the height of the mercury column. Now, how am I going to do that? So let me show you how I can arrange this. I want to get the height of the column in here. Well, the area, okay, so the area times the height. So if this is the height, okay, the area of this tube times the height is equal to the volume of the tube, which means that the volume divided by the height is the area. So I can take and substitute the volume over the height for the area. That doesn't seem to be doing us any good, but if you also realize, if you also realize that density, that's density here, is mass over volume, which means that volume times the density is the mass. I can plug in, just like I substituted for A here, I'm going to substitute rho V, rho for the density times the volume, right? Rho V for M. And that has to get multiplied by G. So now if I look at this, I see, oh, look at this, my volumes cancel here. So I end up with the pressure over the height equals the density of the material, like the mercury in this case, times the acceleration due to gravity. And I just put height over on the other side. I end up with P equals rho G H. And this we call the barometric formula. Okay. And you'll notice in this formula that there is no width. There's no area of that tube. It's actually a closed tube. Well, whatever. So the width is irrelevant for the tube, okay? Which makes sense because the pressure exerted by a gas in a room does not depend on the width of the measuring device. That would make absolutely no sense. So there's no width, there's no area. The width of the column is really not relevant. And so it's very nice that it's not there. Okay, so here is another schematic of the Torachillian barometer. This is the height that we talk about. The height is the height above the reservoir. Okay. And by the way, what's in here? Is there nothing in there? So remember, we started with this barometer that was laying flat, right? Starts out laying flat like this, and you raise it up. So basically the mercury is coming down from the top. because the, gravity is pulling it down to an extent. So there's really no air in there, right? There's no air. What's in there is probably just mercury vapor. There'll be a certain pressure of mercury above that liquid. So that's really all that's there. That's a very low pressure. So it's almost nothing, but not quite nothing. So what I have here is a special problem. Here it is, special problem. I call it special problem 2. This is on the barometer. And I'd like you to do a couple of things in this problem. So what this problem is all about is it's saying that if the pressure is basically 1 atmosphere, that's what this is. If the pressure is 1 atmosphere, 1.01 times 10 to the 5th pascals, then I would like you to prove that the height is 760 millimeters of mercury. Yeah. Or I guess I could say if the height is 760 millimeters. It doesn't make sense to put mercury there. The height is simply 760. If the height is 760, prove that the pressure is 1.01 times 10 to the 5th pascals. This is really what I want in this special problem. And you could see that it sort of walks you through some of the things we've done. So first, I'd like you to show that a pascal is also equal to a kilogram per meter second squared. This was really done in class already. We did that. And then now show that if the height is 760, the pressure is this. Okay, so basically what you have to do here is use your rho GH, right? P equals rho GH, but you need to plug in the correct density, G, and height to make this come out in Pascal units. All right, so that means since the Pascal is a kilogram per meter second squared, that means that your density is going to have to be in kilograms per cubic meter, and you're going to have to convert it. You have to show that conversion. And the height will end up in meters, right? So you have to figure out what 760 millimeters is, how many meters. It's pretty easy. And then you'll have to use G in still meters per second squared. That doesn't change. That's in appropriate units that are compatible with the unit of the Pascal. So it's really a units exercise to put this all together and to show how 760 millimeters goes with 1 atmosphere, or 1.01 times 10 to the 5th pascals. And finally, I'd like you to look at how high a column of water would have to be. And the only difference in this calculation is the density. Okay, and you should remember that a milliliter is a cubic centimeter. You need to know that to do your conversions. Okay, so that's basically a units exercise. Okay, so moving on, let's see. So this is how you measure barometric pressure. I already showed you this. This is a Torachillian barometer. But what if you have a sample of gas in the lab? All right, now what I'm showing you here is a manometer. Okay, manometer. And you could see that there are 2 levels. Here you could see the mercury levels, and they're the same. And what you see here is this plastic tubing that comes onto the top of one of the ends. So this is the end of one of the tubes. And the end of the other tube, this is open to the atmosphere. So a manometer has one end open to the atmosphere. This is what we call an open-ended, which most manometers in labs, old ones that are made of mercury, are open-ended. And then this tube, this piece of tubing here, goes off to a gas sample somewhere. probably right now the tube is open to the atmosphere because these levels are the same, but you could put a flask on here and you can put a gas sample on this piece of tubing. Okay. I have a nice schematic of it here. This is an open-ended manometer. All right. And so you would have this valve here would lead to a gas sample. Okay. So how do you measure, what is the pressure of the gas in the gas sample that's hooked up to a manometer? How would you figure out the gas pressure? Well, if you look at this situation here, what you have is you've got the atmosphere pushing down on one side. Remember, this is open. So it's atmospheric pressure pushing on that side. But on this side, it's the pressure of the gas that's pushing down. So the first thing I'd like to ask you is, which is greater? The atmospheric pressure or the gas pressure? And which is greater? Well, the greater pressure is going to push down harder. So you could see here that the gas is pushing harder. So that tells you that the gas pressure is greater than the atmospheric pressure. And the difference between the heights in the column here, in the two columns, is equal to the difference in the pressure of the atmosphere and the gas. But the reason I ask you which is greater is because now I can decide, say that P gas minus P atmosphere is positive, because I know that P gas is greater than P atmosphere. And that means I can take and subtract the higher number here from the lower number here, right? And that will give me, so that equals the height difference for each of the two columns. So let me just do an example for you. Where's that example? Did I forget to do it? I'm just going to pause this for a second. Boy, I wish I could pause class like that when I don't have a slide and just go and get it. So this is my example slide here. So in this picture, you can see that P gas is greater than P atmosphere because it's pushing harder, just like the picture up here. And the difference, all right, so now I take 32.5 centimeters and subtract 21.3. That's 11.2 centimeters, which is 112 millimeters. So now I know that P gas minus P atmosphere, which is positive, is 112 millimeters. So you're given that the atmospheric pressure is 750. So 750 plus 112 is 762 torr, or millimeters. Okay, so that, oh, did I do that? It's 862. Great, sorry. Okay. So now, okay, what if we had the opposite situation? So here's your gas. And now let's just flip the numbers here. Let's say that this and this were like this, and this is 32.5 centimeters, and this is 21.3 centimeters. And here's your gas. Now we see that P gas is less than P atmosphere. So P atmosphere minus P gas is what's positive. So P atmosphere minus P gas is 112. Okay, so move P gas to the right, move the 112 to the left. Now you're subtracting. So instead of adding here, you're going to subtract. Oops. And that S comes out to whatever 750 minus 112 is. 740, 738. Is that right? No, it's 638. Made the same mistake again. Okay, so you have to kind of pay attention to which side is higher. By the way, nowadays in labs, you'll see all kinds of gauges that are digital, although they're really not as good as that old barometer. Okay, and by the way, if you make a, oh, never mind. All right, so all of that, and we've done V, N, and P. Okay, so I'm going to move on to temperature. Okay, temperature. Okay, so temperature is last, but definitely the most difficult concept really to understand. And also, of course, it's the most important for thermodynamics. So we spend a little bit of time here on temperature. And so temperature is defined in such a way that in a way that has to do with heat transfer. So what we do is it's basically the sort of definition goes like this. If two objects are placed together, in other words, they're in contact, okay, and heat flows from object A to object B, then we can conclude the following. We say that A is hotter than B, or at least it started out hotter than B. In the end, they end up being the same temperature. And we say that A is at a higher temperature than B. Okay. So schematically, you have, they say, two objects that are touching one another. Q represents heat, and heat is flowing from A to B. Okay, so this implies that TA is greater than TB, where T is the temperature. Okay, if there is no heat flow, what could you conclude then? Well, no net heat flow, I should say, because there'll always be heat flowing in each direction. No net heat flow. Then you'd say that the temperatures are equal. And the fancy term for this, because they're touching and there's no heat flow, is that they are in thermal equilibrium. Use that word a fair amount in this course. Okay, so you could see that the concepts of temperature and heat are closely related. But temperature is not heat. They are not the same thing, right? Well, this leads me to talk about something that's often called the Zeroth Law of Thermodynamics. I bet it's called Zeroth Law because it came after the first law and the second law. And they didn't want to rename the first law and the second law, so they just named it the Zeroth Law. So here's my go at the Zeroth Law of Thermodynamics, okay? It's like transitivity of temperature in a way. If A is in thermal equilibrium with B, and B is in thermal equilibrium with C, then A and C are in thermal equilibrium. Okay, so I guess you could picture that as A, B and C sort of lined up here. But I believe that that this whole idea doesn't just refer to things that are next to each other. This kind of supports the temperature concept and allows for thermometer use. So supports the temperature concept, but also allows for thermometer use. So let me tell you a take on this zeroth law. So let's say you have two ice baths. Ice water baths. So here's the ice and the water, okay. And then you have another one over here. Okay, so this one I'm going to call A, and this one I'm going to call C. All right, now, place thermometer. Thermometer is object B, okay? Place thermometer, which is B. In ice bath A. What happens? Well, the mercury or whatever's in the thermometer, the liquid in it, goes up to a certain height. Okay. A and B are in thermal equilibrium. And when they're in that equilibrium, the liquid in B goes up to a certain height. Now, take thermometer B. So I would say liquid rises, probably falls if it's an ice bath, to a certain height. Now, place thermometer in ice bath C. So I'm going to take this, put it in here. Okay, and the temperature of B is indicated by this height because we have this liquid expands and contracts according to the temperature. Obviously, you use thermometers. Well, actually, you don't use them too much more anymore. We use these temperature probes, but anyway. Okay, so you take that thermometer B, you place it in bath C. If it rises to the same height, that indicates the same temperature, okay? And it's in equilibrium with bath C now. So it means, so the conclusion is that A and C have the same temperature. Okay, which just seems kind of long-winded and obvious, but people thought about these things, and it's kind of important for the concept of temperature. All right, so that brings me to the whole idea of temperature scales. And you know that in science, we use very often degrees C, that's the Celsius temperature scale. In the USA and in Britain, we use the Fahrenheit scale. And I don't think I'm going to say much more about this because we don't use Fahrenheit in this class, but we do use the Kelvin scale. And the Kelvin scale is called also the absolute temperature scale or the thermodynamic temperature scale. And you know that you can go back and forth pretty easily between Celsius and Kelvin. Temperature in Kelvin is the temperature in degrees C plus 273.15. So 100.00 degrees C is 373.15 Kelvin. That's the boiling point of water. And you know, of course, the freezing point of water is 273.15 Kelvin, freezing point of water. Did you know that 1 degree C is equal to, this is the size of a degree, is equal to 1 Kelvin? Well, that's why it's so easy to transfer back and forth between Celsius and Kelvin. It's because the sizes of those degrees are the same. And Fahrenheit is actually only about half of a Celsius degree. That's what makes that whole equation between Celsius and Fahrenheit, that conversion, possible. Very, very difficult, actually. But we don't even do that in this class, to tell you the truth, because we use only Celsius and Kelvin. All right, so I have all these names for the Kelvin temperature scale. Kelvin, absolute, thermodynamic. This is the one that we use in 405 whenever we use equations. Basically, we use the Kelvin temperature scale. Does anybody know why is the Kelvin scale so big a deal, so important, or so special? And I know that if I were in class, I would have at least a few people raising their hands and telling me that Kelvin scale is the 0, and the Kelvin scale is as cold as it gets. Actually, it's a little colder than it gets. No one's ever gone down to 0 Kelvin. So we say that 0 in kelvins is absolute 0. There is no such thing as a negative temperature in Kelvin. Okay, and I just want to give some space here. So then I'll go there. All right. Also, I just want to let you know it doesn't get any colder. I told you this. But did you know that scientists have really tried very hard to get colder than Kelvin, even to get to 0 Kelvin? And so let's see. The last time I looked this up, which was after 2014, well after 2014, but in 2014, there was this cryogenic underground observatory, which is in Italy. And I found it in a list of rare events. And okay, so on 10/22/2014, they got down to minus 273.44 degrees C. So they'd have to get 0.3 of a degree cooler to get to minus 273.15. And they were unable to. Okay, so anyway, so they've tried and failed. And so we say that that's absolute 0. So at least in this part of the course, from our point of view, Kelvin is special because of the gas laws. And I'd like to talk about Charles' law because it really is very relevant to this first of the gas laws that I'm going to discuss. So Charles' law says if pressure is held constant, and I'm going to have quite a discussion about what this means in a few minutes. If pressure is held constant, then volume is proportional to temperature, okay? So what this law refers to is cooling a gas at constant temperature, constant pressure. So if you take a sample of a gas that's held at a certain pressure and you decrease the temperature, right? So here's a graph, and you start here, let's say, and you decrease the temperature. So you're going backwards here. The volume goes down. So V goes down as T goes down. If you started at a different pressure, it would go down along a different line. At some point, that gas, as you lower the temperature, what's going to happen is it's going to liquefy. So at some point, the gas turns to liquid. So you get a whole bunch of points, and then at some point it liquefies, and then you just extrapolate. If you extrapolate that line and hit the x-axis, it hits it at minus 273.15 degrees C. So now let's say you do it at a different temperature, and then at some point you get liquefaction, and lo and behold, all of these lines of decreasing volume as temperature decreases, they all coalesce at one point, minus 273.15. Okay, but if we look at Charles's law, it says that there is a proportionality between volume and temperature. What a proportionality means is that so this proportion means V proportional to T means V is a constant. Let's call it a constant times the temperature. But this line here, there's actually an intercept. This is the y-axis here, and it has an intercept. So in Celsius, we do not have a proportionality. The equation, this is actually the equation for these lines with somewhat different slopes and different intercepts. So we don't have a proportional relationship. A proportional relationship would have to go through the origin. We instead have a linear relationship. Right? Because we have a non-zero intercept. Okay. So what chemists have done, physicists actually, is they say, okay, well, what if we just move this axis over? So instead of this line being over here, we just move this axis over to this point here, this negative 273.15. And that's exactly what this shows here. So move the axis over. Well, this is equivalent to a new temperature scale. Okay, because now what was negative 273.15 is now 0 Kelvin. By the way, in Kelvin, you don't use the little degree symbol. You just say 0 K, 125 K. instead of degrees C, we use just the K, but that's a technicality. And now all those lines that coalesced at negative 273 are coalescing here at 0. And the equation here is volume is just a slope times the temperature, which is a proportionality. So my point being is that volume is only proportional to temperature if Kelvin units are used. Okay, so if you don't use Kelvin, any problem that involves Charles's law is going to you're going to get the wrong answer. You use the wrong type of units. So if temperature is in Kelvin, then V is proportional to T at constant pressure. This is Charles's law. It is not valid unless Kelvin units are used. So if V equals a constant times the temperature, then V over T is a constant. And that means if we have one situation, one set of conditions. We find V over T. We know that it will be the same as long as pressure doesn't change. That a second set of conditions. So we would say V1 over T1 is V2 over T2. And this is another way of looking at Charles's law, as long as the pressure is constant. Okay, so now I want to sort of, in Gen Chem, I probably would have said enough, Now I'm going to elaborate on this constant at constant pressure. So what I'd like to do is talk about what happens from the microscopic point of view. Remember, microscopic means when we're talking about the molecules or the particles. Okay, so from a microscopic point of view, why does the volume go down as the temperature goes down, or why does volume go up as the temperature goes up? Right, same thing, volume goes down as the temperature goes down. Okay, but I'm going to give you going up as this example. Okay, so first of all, let's picture, I do this a lot in P-Chem, where we have a container with a movable wall, right? So this is like a movable wall. Okay, and so it's like a piston, but it has this part that can go up and down. And we always idealize this. We don't, if they ever think about the mass of the cover or things like that. Okay. So let's see what's going on. Okay, we have this container. Here's the top of it, right? And what I'd like to know, okay, so we know that the outside pressure is the atmospheric pressure. I'd like to ask, what is the pressure inside? Okay, so here's the thing. If the wall is not moving, then what do we know? Then we know that the pressure inside must equal the pressure outside. That's what we call mechanical equilibrium. Okay, so P inside equals P outside equals atmospheric pressure. So they would be equal if the wall is not moving. So third, I'd like to say, what does the inside pressure come from? What is it due to? And I don't know what you would answer if you were in the class, but some of you might say, there's molecules in there, right? And those molecules are moving around and they're striking all the surfaces. They're going in all different directions. Okay. And so what is the pressure due to? It's due to collisions of the molecules or the particles with the walls of the container, the inside walls. And if the wall is not moving, then the pressure inside and outside, these pressures are equal if the wall is stationary, not moving. Okay, so I'm just setting it up now. I haven't done any heating or cooling yet. So now I'd like to increase the temperature. So what happens when the temperature goes up? Well, maybe you remember from general chemistry that when the temperature goes up, the molecules move faster. So this actually has two consequences. One of them is that there will be more collisions with those inside walls. And another one would be that the collisions are stronger. And these are forces, right? These particles hit with forces. So the pressure inside has to go up, at least temporarily. So what you have is, after heating, you have a a pressure imbalance. So right after heating, you still have P atmosphere, but now the pressure inside has gone up. Can it stay that way? What's going to happen is that because this force is greater, this piston wall will rise. Okay, the piston goes up. And as it goes up, the pressure inside is going to go down. Why? Because you're opening up a greater area for the same particles to hit. Okay, so as the gas expands, the pressure inside drops. So when does the expansion stop? When P inside, again, equals P atmosphere. So when these are equal. Okay, but look, the gas has expanded. Volume is greater. Okay, so why am I telling you this? It's because we have this Charles's law. It says volume is proportional to temperature at constant pressure. Okay, but there's a lot of different pressures in this problem. There's the atmospheric pressure that's pushing down on the outside of the gas, on the piston. But we also have the pressure of the gas inside. And the pressure of the gas inside, when you heat this thing, the pressure goes up inside temporarily until that gas expands. Right now you have these more forceful collisions and more of them, but you have a greater area of the walls and force per unit area, right? So you're increasing that denominator, you're decreasing the pressure. And so at the end, P gas is again equal to the atmospheric pressure, which has not changed. So it is against a constant atmospheric pressure, but understand that the pressure of the gas is not constant throughout this process. That what actually drives the expansion is that pressure imbalance. So it's the pressure imbalance that drives the expansion. If you didn't have that pressure imbalance, this gas would not expand. Okay, so we say volume is proportional to temperature at constant pressure. Okay, and realize that the pressure of the gas is the same at the beginning and the end, right? The external pressure, the atmospheric pressure, is constant throughout. So I hope you have a little better understanding of that than before. Okay, so what if I look at some other things that can happen with gases? So let's say I have a container and I have a bunch of particles inside the container and they're moving around, right? And then I heat it up. But now there's no piston, there's no movable wall. Volume is constant. So I'm increasing the temperature, all right? So what's going to happen is, again, these particles are going to be moving faster. So I'm going to show larger arrows representing their motion. Faster motion. But I haven't changed the area at all. I've increased the forces on the inside walls. So pressure goes up. Okay. So if the volume is constant and temperature increases, the pressure increases. And I call this, no, that's different. Okay, wait. So that's another unnamed law. Then there's one called Gay-Lussac's law, which actually is also called Avogadro's law. But I like to call it the Deflategate law, after the New England Patriots, which says that pressure is proportional to temperature if the volume is constant. Yeah, I guess that's what this is actually. It's not a different one. That's the one I was talking about here. So pressure is proportional to temperature. Of course, when the footballs went outside, the pressure was lower because they went outside. One could argue about how much that pressure would change. I actually spent many minutes calculating things, maybe even hours, to see what was reasonable. And I think that if Tom Brady had said, pressure is proportional to temperature, of course the pressure is lower outside. You know, if he knew that from high school or college, then maybe that would have nipped the whole thing in the bud. But anyway, so P over T is constant, which means P1 over T1 equals P2 over T2. Okay, so that's another law. And so we have that the volume, let me get a little more space here, volume, temperature, and pressure temperature relationships. These are very simple. These are proportionalities. But now we come to the relationship between pressure and volume. Okay, and I actually have a syringe. Let's see, showed you this in class. So I have this giant syringe. Here's the syringe. Okay. And everything is left right for me, so I don't know quite what I'm doing, but basically, if you push on a syringe, I'm gonna do it this way. As you push this down, it gets harder and harder to do. I really can't do it much further than this. Okay, so basically, first it's easy to push, and as the volume gets smaller, it gets harder and harder, and that's because those molecules in there are fighting back more and more. The pressure is going up in here, and that's why it becomes harder and harder to push in this syringe. So hold on, let's go back to the notes, and I have a cute little illustration here that I use in general chemistry. A syringe with somebody's thumb. I'd hate to be the person whose thumb is held there, but you have a volume. You know, when you haven't really pushed it in, it's just sort of relaxed like that. And then you start pushing it in, decreasing the volume of the air, and it becomes much harder to push. I would say the gas is fighting back. It's because you've got this greater concentration of gas molecules and they're colliding with the walls more often. We're going to look at how pressure depends on collisions, I think in class starting next time. And so the gas pressure has increased. So you see that we have this this inverse relationship between pressure and volume. As the volume increases, the pressure decreases. And this is an inverse proportionality. So if P is proportional to 1 over V, we have PV is a constant. So P is a constant times 1 over V. So P times V is a constant. And that leads us to P1 V1 is P2 V2, which is Boyle's law. Well, this is also Boyle's law. So when we look at a graph of P versus V, you know, up here, I didn't talk about, I talked about a graph for Charles's law. I said that, you know, I showed you how that was a straight line. Where is that? Right there, right? Straight line. VT is a straight line. In Kelvin, it goes through the origin. P versus T would also be a straight line. But when you look at P versus V, you don't get a straight line. You get a curve. It's an inverse proportional curve. Okay, and so let's see. I didn't mention it, but it's very important for me to have said that this happens at constant temperature. Okay, so when I pushed in the syringe, the temperature in the room wasn't changing. Of course, I didn't measure the pressure, but it would have been an inverse proportionality. So this curve here is for a particular temperature. Let's call it T1. Okay, if we change the temperature, we're going to change the way the pressure behaves, because now we know that pressure goes up, say if the temperature increased. So it wouldn't look exactly like this. So at a higher temperature, so by the way, we call this an isotherm. This is a PV isotherm. And that's because iso means constant. Now, supposing we had a higher temperature. So supposing we now, you know, looked at how does pressure vary with V at some higher temperature. So here's a particular volume on this graph. If we raise the temperature, we would raise the if we raise the temperature, we would raise the pressure. So maybe the new pressure would be over here. And then we would have a new isotherm. This is another isotherm. This would be, say, a T2, where T2 is higher than T1. I know it's higher because because here I have a certain pressure, right, at the lower temperature, and here I have a greater pressure. This is a greater pressure at a higher temperature. So I know that at a higher temperature, I'm going to have isotherms that are, you know, going up and up this way, and lower temperatures, I would go this way. All right, so there's really a whole set, like an infinite set, really, of isotherms, which show the behavior as T changes, shows how pressure changes with volume as the temperature increases. Okay, so there's those PV isotherms. All right, so another thing about Boyle's law, which I'm sure you did not learn in general chemistry, is that it is what we call a limiting law. And that is to say that it is not valid at all pressures. It's only valid at low pressures. It's valid in the limit as the pressure goes to zero. Okay, so that's why we call it a limiting law. Okay. We call gases ideal. So gases are ideal when Boyle's law holds true. So you might ask, you know, it's valid at low pressure. What's a low pressure for a gas? So what's a low pressure? Where is this law valid? And so you can be very comfortable in saying that 1 atmosphere is pretty low for all gases. Because we'll realize that as we start to look at different individual gases, you know, that they do have individual properties. They might attract each other at certain conditions, and that makes them not obey Boyle's law, that makes them non-ideal. Okay, but to a first approximation, at 1 atmosphere, pretty much all gases behave ideally. They obey Boyle's law. 10 atmospheres, most gases are still quite ideal. It's really at very high pressures when gases start to deviate from ideality and show their individual characteristics, which really sort of brings us to Avogadro's law, which is the last of the individual gas laws. And it deals with the relationship between volume and moles. Okay, so there's already 2 parts to this law. I say the first part is at constant temperature and pressure, equal volumes of gas contain equal numbers of moles. And this is regardless of gas identity. This is true when the gases are ideal, right? And that's at somewhat low pressures. The second part of this law is that the volume is proportional to the number of moles. Okay, so that means that any gas, 1 mole of any gas has the same volume at the same temperature and pressure. Of course, when you're at pressures where individualities between different gases come into play, this is not going to hold either. But when gases behave ideally, this will be true. And we have a particular set of the situation we call STP, standard temperature and pressure, which is 273.15 Kelvin and 1 atmosphere. And the volume of any gas is 22.4 liters. And how do I know this? I use the ideal gas law. So let me show you where the ideal gas law comes from. PV, well, okay, let's start with the fact that V is proportional to moles. V is proportional to 1 over P. P is proportional to 1 over V. I just rewrote it. Volume is proportional to temperature. So that means we take all these together, that the volume is proportional to moles times temperature divided by pressure. And the proportionality constant is this gas constant, R, which is 0.082057 liter atmospheres per mole Kelvin, or in bar, liter bar per mole Kelvin. So generally we use this one, 0.08206 is what I generally use it as. And that means that you have to have your volume in liters, your pressure in atmospheres, and your Kelvin temperature, of course. Well, this is often rewritten as nRT over P, or PV equals nRT, which is the ideal gas law. Oops. Affectionately known as the ideal gas law. Okay. So I'm almost done for today. What I really just want to show you here is the gas density worksheet. So I'd like you to go home and do this worksheet. It's not that long. What it is it's showing you the kind of manipulation. So I guess I should first say that, you know, you're expected to know how to do all kinds of gas problems. Some are in the homework. You might have to use PV equals nRT, or V1 over T1 is V2 over T2. P1, P1, V1 equals P2, V2. You can put these laws together. This is what's called the combined gas law. So I expect you to be able to do the same kinds of problems that, you know, you did in general chemistry. I'm not going to go over a lot of them in class because this is PChem. But an additional thing that I like you to be able to do in PChem is to sort of start with an equation and then find a different relation. That's a very closely related relation. So I'm asking you to use this equation to find a relation between gas density and molar mass. And I kind of go through some guidelines here. I sort of go through this problem with you. And if you want to look and see this done out, if you go to the, let's see, did I write it down? If you go to the video for September 14th, 2020, it's at the beginning of that video that I go over this short derivation. Okay. And you should be able to come up with it. The equation I'm looking for you to get is this one, where this is the density and this is the molar mass. Okay, so that's all I have to say for today. And that's it. See you next time.